Yeah. Okay. So, hello. Today, the first talk in the new seminar series, Introduction to Knot Theory, will be given by Dr. Seongjeong Kim. So, he's an associate professor at the Jilin University in the Department of Mathematics, and he will give three talks. And the first will be today on basic notions of knot theory. Okay. So, yeah, please
Thank
start.
you. Let me start. Nice to meet you. I'm happy to give a talk in topology and geometry seminar. I will give three talks, and basic goal of my talk is to introduce how knot theory is related with low-dimensional topology and other area. As I wrote in the abstract, knot theory is, of course, knot theory itself is interesting, but mainly knot theory is used as a bridge between low-dimensional topology and other areas. So, in the following in three talks, I will explain what does it mean, why we say knot theory is a bridge between low-dimensional topology and other topics. So firstly, today I will talk about basic notions for knot theory, and next time I will talk about the relationship between knot theory and low-dimensional topology. And in the last talk, I will show how, in which sense, knot theory is related to other research area. Mainly the statistical mechanics, so-called introducing so-called quantum invariant for knots. So anyway, firstly, let me start with the basic notions of knot theory. And in knot theory, knots are really common things in our life. Really, literally, it is not. So in sorry, let me try to draw one figure. If you look around in your room, there are some instruments with long electric wires, and mainly those wires are knotted in this manner and in this manner. And we call they are not, literally not. So our goal is to distinguish those two such knots up to such a deformation, where if we stretch or move those arcs by stretching or by moving these arcs, if we can change one to another one, then we will say they are equivalent. But of course, in that deformation, cutting should not be allowed, because if you cut knots, then just cut and a knot and attach again, then you always make it to straight line. So we do not want to such a situation. So in knot theory, our goal is really simple, as I said, to distinguish knots. But let me write formal definitions for knots and the equivalence relation, which I explained in mathematical way. Firstly, a knot of course, in our life, usually we need to care R3, or sometimes it's one-point compactification S3. Is a smooth embedding of S1 into R3 or S3 as well as the image of embeddings. I cannot sure all of you are familiar with the notion of smooth, but actually it is not important in this level. Just think it is a map from S1 to R3, and the image is literally smooth like this. And link in R3 is also smooth embedding, but disjoint union of S1 into R3. Then how we define the equivalence relation? Two knots or links K1 and K2 are equivalent, denoted by K1, K2, if there exists a isotopy R3 times 0, 1, R3, such that, firstly, its restriction R3 times T to orientation preserving male, and secondly, its restriction to zero time is identity, and in the one level, it sends K1 to K2. If there is such an isotopy, then we will call two knots are equivalent. Here, I guess all of you are familiar with homotopy theory, but here, one interesting thing is we compare one-dimensional object in R3, but we consider equivalence relation by homotopy of the ambient isotopy. And if I explain why we care R3, it is because when I say some real life thing, we don't want to cut the object, the knot. But if we consider homotopy from S1 times 0, 1 to R3, then those crossing can passing through itself. So to avoid such a situation, we consider the isotopy of the space where the knot appear. And it is quite important point in knot theory when we consider the relationship with low-dimensional topology. Then, in this manner, we can define knots and links and the equivalence relation. But of course, if we stop here, then stop here and start to study knots and links, then theoretically it is possible, but it is not easy to study because really abstractly they are defined. But in knot theory, there is one way to represent knots, which is called diagram. What is diagram? For knot in R3, let's say it is K. If we project this knot onto a plane, then it will have such a image. We will call this image a shadow of K. And then this shadow always have such a covalent vertices. And for each covalent vertex, we replace it to such a intersection by considering the height of those arcs with respect to the vector where we project K along. So in this crossing, in this part, the projection is associated to this four-valent vertex, and we can say that this one is higher than this part. Then, by cutting lower arc, we present the height of those two arcs, and we call this a crossing. And this one is called overcrossing, and this one is called undercrossing. Then by replacing all four-valent vertices by crossing, we can obtain such a figure, which is called a knot diagram. DK. Here, one thing, maybe you can call it is also link diagram. But as a convention, we do not distinguish knot and link diagram, just call knot diagram, because our theory is knot theory. And in the diagram, because we cut arcs to represent which one is lower, which one is higher, this figure separated to finitely many curves, and each curves are called arc. Then for any knot, we can obtain knot diagram. And naturally, for a given knot diagram, we can obtain a knot in R3. Moreover, the equivalence relation for knots can be presented in combinatoric way. What does it mean? Let's say K1, K2 are links, and dK1 and dK2 are diagrams of K1 and K2 respectively. Then K1 and K2 are equivalent if and only if dK2 can be obtained from dK1 by a finite sequence of the following local deformations. First one is where some curved arc can be changed locally, curved or less curved like that. And second one is such a curve can be removed. And third one is two crossing can be cancelled. And fourth one is this one. I think intuitively it's not difficult to say if two diagrams are one diagram can be obtained from another one by using the following rules, then corresponding knots are seen, and the opposite also possible. And here, the left one is called plana via M, and the right one is called by the Meister moves. And number 1, number 2, and number 3. So, as I said, the goal of knot theory is to distinguish two knots and links in R3. And the equivalence relation is defined by ambient isotropy, but this theorem say actually it is enough to study diagrams up to such a local deformations in finite way. And here I want to make one small remark. Here, this is my personal perspective, but I think it is quite important point of view. The importance of Reidemeister theorem, there are really many. There are really many kinds of importance, but in my point of view, why this is important? This cause theorem topological objects here in the beginning, the definition of knots are just a continuous embedding of the circles. But thanks to Reidemeister theorem, it changed it to combinatoric things. Here, say, we just draw diagrams with finitely many crossings, and they say two knots are equivalent to one, and then if and only if corresponding diagrams can be equivalent up to finite sequence of finitely many moves. So it is more easier to deal with than just say where it is embedding of circles. And I think this is one point why knot theory was popular in the late of 20th century. Okay, let me show some examples. Firstly, such a circle without any crossing is called trivial knot, and this one is called trefoil. This one is called figure 8 knot. And for this one, there are two circles, and this one is called hoop link, And the last one is called Borromean ring. Here now, we didn't care about the orientation, but for circles, we can give orientation. So we can define oriented version of knots and links and cancellation. An oriented link is a smooth embedding of S1 with orientation. Then two oriented links, knots and links are equivalent if one can be obtained from another one by orientation homomorphism and such ambient isotopy. Then the diagram also have orientation like this. Hello? Oh, okay, yeah. Orientations. And then the right dimensional of C. The right dimensional moves, the number of right dimensional moves increase. I mean, up to orientation. Here, plus. For each arc, we can give the orientation. So for this one, there are 4 possible orientations. Here, there are 8 possible orientations, but just up to orientations. And oriented rings are like this. And in oriented
Hey,
case,
Kim.
huh?
So there is a lagging between your voice and writing. So writing comes after a slight delay.
Yeah,
Is it
I
at least
also
for me? I don't know for others.
okay. Let me try to combine, or let me do like this. I open the microphone in my iPad and turn off the sound in the
Yes.
computer. Yeah. Let me.
Right.
Hello, can you hear me?
Yes, yes, I can hear.
Oh, hello.
Yeah, yeah.
Hmm? Okay, I think now fine. Okay. Yeah. Let's see what. Okay. Now is it better?
Yes. Yes. Now
Yeah.
I get.
Okay, then for oriented case, we can define signs for crossings. For each crossing, there are 2 possible orientations given like this. Of course, up to rotations of crossings. Then in the left case, we give +1. On the right one case, we give -1. And this one is called crossing sign of crossing C. Then how we define the orientation? Firstly, we assume that the orientation of the plane is given like this. And then for each crossing, we give vector v1 for overcrossing and v2 of undercrossing. Then if v1, v2 disordered orientation agrees on the given orientation, then we say +1. If not, we give -1. Yeah. Till here is the basic notions to before study knot theory. And then let me write one more time. Our main goal one more time. Firstly, our main goal in knot theory is to distinguish knots and rings in S3. And thanks to Reidemeister theorem, it is enough to study to look diagrams up to finitely many local moves. But usually it is not easy to see. Let me give my favorite example. Let me draw such a diagram. And the question is, what is this? I mean, here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 crossings. But can we reduce the number of crossings? And what is the simplest version of this diagram? And more the easier question is it equivalent to trivial? Actually, at the first glance, it is not easy to see. But the answer is yes. So, well, I think it is not. I have not enough time to show the process, but maybe you may try to deform left one to the right one by using Reidemeister moves. Let me show just the first the starting point of the deformation. Firstly, we take this diagram, and then here we have this part. We apply Reidemeister move 3 here. Then we may obtain such a figure. And then I will apply Reidemeister move 2 here. Then we remove 2 crossings. and do similar things further and further, in the end, you can obtain trivial knot. It means by that is, if we say this one is diagram of one knot and this one is the diagram of trivial, then K1 and the trivial knot are equivalent, because one diagram can be obtained from another one by finite sequence of Reidemeister moves. But next question is that I draw several examples, and the next simplest version of diagram is this one. Can we deform left one to right one? To show they are equivalent, it is enough to show that one diagram can be obtained from another one by finite sequence of Reidemeister moves. But if not, how we can do? I believe that, of course, I believe that you cannot deform left one to right one. You cannot. But is it enough to show that they are not equivalent? Actually, no. Even we cannot success to deform left one to the right one by finitely many Reidemeister moves. Maybe some other guy can do, where 100 years later, 1,000 years later, like that. So now we cannot deform one to another one. It's not enough to show that they are not equivalent. So here we need invariant of knots. Then what is the invariant of knots? It is a map from the set of equivalence classes of links up to isotopy to a set of maybe groups, numbers, polynomials, and so on. That is, if K1 and K2 are equivalent, then their images are same in this set. And this one is called an invariant of knots and links. But again, thanks to Reidemeister theorem, there exists one-to-one correspondence between links and equivalence class of knot diagrams up to Reidemeister moves. So instead of this part, we will define a map from here to here. Then, in natural way, we can obtain knot invariant. So to achieve our goal, to distinguish knots and links, we in knot theory, usually people study how to construct such knot invariants to distinguish knots. And today, I want to show one invariant, which is called coloring invariant. Oh, excuse me, let me bring some water. I'm sorry. Sorry, let me continue. The coloring invariant is defined in the following way. Let D be an oriented diagram, and let's say AD is the set of arcs of D. For example, let's say we have such a knot diagram. Then this knot diagram has three arcs, A1, A2, and A3. Then a proper 3 coloring is a map P from AD to set of three numbers or whatever is the set with three elements, satisfying for each crossing. There are three arcs near to it. Then the image of AI, AJ, AKR, same. Sorry. Or they are different. If there is a map satisfying such condition, then we call the map a proper 3 coloring. For example, in our case, if we say this one, this one, and this one, 0, 1, 2, first possible proper coloring is this one. Then for each crossing, each arcs are colored by 0, and all of them are same. So this it is possible to color diagram with one color, and this one is called trivial coloring. Of course, this can be the color can be 1 or 2 also, or we can color it by 0, 1, and 2. In this case, again, we colored arcs by 3 colors, and moreover, for each arcs, the colors of 3 arcs are different. This is also a proper, of course, non-trivial, proper 3 coloring. And if D has a non-trivial proper 3 coloring, then D is called 3 colorable. Okay, let me show one more example. Now let's take the figure 8 knot. Oh, sorry, before that, let me show. For trivial knot, there are 3 trivial proper 3 coloring. But of course, there are no crossings, so there are no non-trivial 3 coloring. So it is not 3 colorable. But for this diagram, as we saw, there exists non-trivial proper 3 coloring. So it is 3 colorable. But if we take figure 8 knot, then what happened? In this case, sorry, let me. If we start with 0 and 1, to obtain non-trivial proper coloring, this should be, to obtain a proper coloring, this should be 2. Then this should be 1. But you can see that at here and here, the rules are broken because, if we get the proper 3 coloring, then all 3 colors near to crossing are same, or all of them are different to each others. But here, you can see this one different, same, and this one and this one same. So this is not proper 3 coloring. And of course, if you try, and you can try other combinations, start here, you start with 0 and 2 or 0, 0, whatever it is, but it is not possible. So later, you may see that there is no non-trivial proper 3 coloring. That is not 3 colorable. Then why I introduced such a proper coloring? It is because of the following lemma. 3 colorability is preserved under Riedmeister rules. In other words, if D and D prime are equivalent and there exists a proper 3 coloring, then they uniquely exist proper circling for D prime corresponding to D. That is, the three colorability is invariant under Rademacher moves. So here we can see in this example, trivial knot is not three colorable, but platform knot is three colorable. So they are not equivalent. Similarly, middle one and right one are also not equivalent. But we don't know how about the trivial and figure eight knot, because both of them are not three colorable. Then let me show one simple show the idea of the proof. The idea of proof is quite simple. Since by the definition of equivalence relation of diagrams, one can be obtained from another one by finitely many Rademacher moves. So it is enough to assume that D prime can be obtained from D by one of Rademacher moves. And if D looks like this and D prime looks like this, and let's assume that this sock is named by A and P A is L, where P is the proper three coloring for D. Then we color D prime in the same way inside of this part, outside of the arc, and then we color this A, those two arcs by PA is equal to L, and PA prime also is colored by A, L. Then locally, these are colored by L, these are colored by L, these are colored by L. So it satisfies the condition for proper three coloring. And this part, the arcs in this part, also colored way because they are induced from the coloring, proper three coloring of T. Sorry. In this manner, we can find P prime for the proper three coloring P prime for D prime coming from the proper three coloring P of D. And case 2 is Rademacher move 2 case. Say A, B, C, P prime. Then the situation is same. Let's say P A is L, P B is M. Then we define P prime A is L, P prime B is M, and P prime B prime also M. Then we need to determine the coloring of C, but if L and M are same, then P prime C is equal to L. Then L, 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 L. So both crossings, the coloring near to both coloring and both crossings agree on the rule for proper three coloring. And if not, we take the coloring for C. We take another color, remaining one color for the coloring of C. This is possible because we have third crossings, and here we have 1, 2, and 3 colors. So this is possible. And in some sense, the coloring of C is determined uniquely in both cases. So in this manner, we can find the unique corresponding proprietary coloring for D prime coming from P. And for Riemann of 3, also you can do. Then, thanks to this uniqueness, we can obtain the following theorem. If D and D prime are equivalent, then the number of proper 3 coloring of D and the number of proper 3 colorings of D prime are same. That is, by counting the number of proper 3 coloring, we can obtain an invariant for knots. And this one is called 3 coloring invariant. So coming back to our example, for trivial case T, the number of proper 3 coloring of D is 3, just 3 trivial colorings. But for this one, the number of proper 3 coloring of D is bigger than or equal to 4, because firstly, we can obtain 3 trivial colorings, and then we already found one more non-trivial coloring. So they are not same, so they are not equivalent. And if you are interested in, you may try to color this diagram by 3 colors. Then actually this is equal to 9. But still, we cannot distinguish this one with therefore. To resolve this problem, people think how to make this invariant stronger. Actually, in this case, we used 3 colors, 0, 1, 2. But why we should use just 3 colors? maybe one can use 5 colors or 4 colors, 6 colors, 7 colors, 100 colors, like that. And if it is possible, well, we can expect that the coloring can distinguish more than 3 colorings. So one try to change 3 colorings to P colorings. We want to use some P numbers of colorings. Then, actually in this case, this one is Z3, right? We have 3 elements, so we just use G1, G2, the 3 elements from Z3, and we replace it to ZP. But here we have some problem. In three coloring case, since there are 3 colors and there are 3 arcs near to one crossing, it is easy to define what is the proper 3 colorings. But for example, if we have 5 colorings, then let's say this one is colored by 0, this one is colored by 1, then there are 3 more possible colorings for AK. To avoid such ambiguity, one got such an observation. Here, for 3 colorings, we said all of them are same or all of them are different. But if we replace the set of colorings to ZP, then there exists ZP has a group operation plus. And one noticed that those 2 properties can be obtained from such an equality. P AK is equal to P AG twice minus P AI. If mode sorry, let me change the Q to Q. And if you put 3 here, then this equality gives such a rule for a proper 3 coloring. So we use that equality for Q colorings. A proper Q colorings is a map from the set of arcs to ZQ satisfying for colorings of arcs near to crossings. They satisfy such an equality. PAK is equal to 2 PAJ minus PAI, where this AK is this arc, which is determined by the orientation of overcrossing. I mean, here, overcrossing is oriented like this, then we can say if this one is front, this one is right, and this one is left. Then left one can be determined by the colors of AI and AJ. So we can extend Q colorings for any number Q, but usually we assume that it is prime number. Then we analogously define if D has a non-trivial proper Q coloring, then D is called Q colorable. And Q colorability is preserved under Reidemeister-Moves, and theorem are almost the same with this lemma, with the case of three colorings, and the number of proper three colorings of D is invariant for knots. Then how it works? For this example, let's take Z5 and we color, we give orientation like this. If we color this arc to 0, this arc to 1, then by the rule, the coloring of this part, let's say the coloring is A, then A should be the twice of this color, 2 multiply 1, minus the color of this one, minus 0 is 2 mod 5. So this one should be colored by 2. Then again, here we have another crossing. Then in this one looks like this, and over crossing is colored by 0, this arc colored by 2. Then we need to determine the color of this part. And the color of this part is twice of 0 minus 2 is 3 mod 5. So this arc is colored by 3. Then one can easily check that for those two crossings, the rules for proper PQ, proper 5 colorings are satisfied. That is, it is 5 colorable. But you can, you may try that. Oh, sorry. This one, therefore, is not 5 colorable. So by theorem, we can say that this one is not equivalent to this one. Actually, we can assume that Q is any positive integer number. It is possible, but if you study quandle, this coloring invariant theory a little bit more, then if it is not prime, then it can be decomposed to prime numbers, and the number of colorings of that diagram can be determined by the colors of prime numbers of colors. So in some sense, it is enough to see the prime numbers. That's one reason. And if I say it is more, it is in other words, actually in this case, we use ZQ. And if Q is prime number, then ZQ becomes field. So we can use linear algebra to study color invariant. So usually we assume it is prime number. Let me show one example. Actually, it is a really good question because of the following reason. Yeah. Before that, actually, the number of proper 5 colorings of D is 25. And if you remember the number of proper colorings of trefoil, this is 9. And the number of proper 3 colorings of D is equal to 3. Trivial knot is equal to 3. Then you may feel like this one is equal to 3 square. This one is equal to 5 square. And as an exercise, you can show that the number of proper 2 coloring of D is always q to the k. And the idea is the following. For example, we have those A1, A2, A3, and A4. Proper coloring is a map from X to Z5 satisfying equality for each crossing A, B, C, C is equal to 2B minus C. If I change A minus 2B plus C is equal to 0, then we can write like this. We have four colorings, and we have 4 arcs. Then for each crossing, let's see. For example, in this from this crossing, 2A1 minus A2 plus A3 is equal to 0. So here 0 minus 2, 1, 1, 0. And you will get 3 more things. So to find the proper 3 coloring is to find the solution of this equality. Then this is linear algebra. But in linear algebra, the coefficients, the entries should be elements in field. But since Q is prime, this is in M 4x4 Z5 element. Since Q is prime, 5 is prime. Oh, sorry. Since 5 is prime, G5 is a field. So we can apply linear algebra. So usually we assume Q is prime. Is it? the number of crossings n that Q color is needed, where Q depends on. It is not easy to say. I think no. It is because, for example, here, this is 4 colorings, 5 colorable, and this is 3 coloring and 3 colorable, but this knot is 3 colorable. It has 5 crossings. So I think the Q and N are not depend on each others, I think. Yeah. To be honest, I have no idea. Yeah, I have no idea. Oh no, it is not. It is not. It is not. It is not. If I have a chance, I may tell you, but this Q, well, if I let me say it directly, this Q, because of the linear algebra, this Q is related with the determinant of this matrix. Analogously, for given diagram, you can get matrix, and that the determinant of that matrix gives Q. But the determinant of the matrix does not depend on the size of the matrix or number of crossings. So we cannot say that. It is not related. They are not related. If you are curious, you may solve this exercise with this idea a little bit more. Then you can see that they are not related. Yeah. So let me do a little bit quick. So in this manner, we can extend the coloring as 3 coloring invariant to Q coloring invariant. Yeah, but we want to generalize that concept a little bit more. And the generalization is related with an algebraic structure which is called quandle. When we have a crossing AI, AJ, AK, for simplicity, let me remove P. To determine the number of crossing AK, we used such a thing, 2AJ minus AI. But it means the color of this part is determined by this color and this color. So let's say there is some binary operation star AI AJ. So to generalize this, let's say Q a set and a proper with a binary operation star. And the proper coloring by Q is the map from AD to Q satisfying AK is equal to AI star AG for any crossing. But to obtain a coloring invariant on by Q star, Q star should satisfy then which conditions are required? From basically, they are those conditions come from Reidemeister proofs. For example, for Reidemeister move 1, we want to say the coloring of this diagram induce the coloring of this diagram. Then outside of this part are seen, we assume. Then this part should be colored by A. This one also should be colored by A. But in this crossing, locally A, then by our rule, this part should be colored by A star A. But they are connected. So the star should satisfy such an equality. For any A star A is equal to A. Secondly, for Reidemeister move 2, if this part colored by A and B, then this should be colored by A, this should be colored by A, B, and this one also should be colored by B, because the outside of diagrams are same. The colorings of outside of diagram at this part should be same. Then we need to determine the crossing, the coloring of this part. But here there is a crossing A, B, and C, and B should be C star A. So to obtain coloring, there should be C such that C star A is equal to B. And moreover, do you remember when I talk about the proof of this coloring invariant? I said the color of C is uniquely determinant. And because of that, we obtain this invariant, this theorem. So here, the C should exist uniquely. And this one is second condition. For the last, for Reidemeister move 3, if this part colored by A, B, C, then here also should be colored by A, B, and C. And by using our condition, the end colored by C, B star C, and this is A star B star C. And here, if you do C, B star C, but this is A star C star B star C. Then outside, the colors of outside should be compatible. So here we obtain A star B star C is equal to A star C star B star C. So to obtain the coloring invariant, this algebraic structure should satisfy those three conditions. So we define an algebraic structure. A quandle is a set Q with binary operation such that firstly for any A star is equal to A. For any AB, there uniquely exists C such that C star is equal to B. And third, for any A, B, C, A star B star C is equal to A star C star B star C. And the proper coloring of D by Q star is a map. Then, if D and D prime are equivalent, then there exists one-to-one correspondence. So this gives coloring invariant. Then we can give three simple example. First one is we already know A star on G, take G Q and 2V minus A. Give binary operation 2V minus A. Then this is becomes a quandle, and this is called a dihedral quandle. Or sometimes called Takasaki quandle. And the second one is if we take a group, then G star A with operation B A B inverse is called a conjugation. And if we take a Laurent polynomial ring with variable t and give a binary operation ta plus 1 minus tb, then this is called a Alexander quandle. There are such examples of quandles, and the coloring of by each quandles gives several invariants. In particular, the coloring by Alexander quandles gives polynomial invariant also. So this is one algebraic structure to obtain not invariant as a generalization of three coloring. And the coloring invariant is really easy to count because just try and we can distinguish. But it is quite strong. In particular, if we extend it to quandle, then it is a little bit more, it is a little bit stronger than before. So I think I already do a long time, but please give me 5 minutes more to introduce so thank you. One interesting invariant, which is called not quandle. Actually, quandle was in the one of popular topic in nursery for a while. It is because of the following thing. Firstly, we define quandle induced from a given knot. For a knot K, we consider S3 minus NK. This is tubular neighborhood of K. Then we fix one point like the fundamental group. And let's say this is K, then this is the tubular neighborhood of K. And we consider arc from here to the boundary of tubular neighborhood. And let's say this is alpha. And since tubular neighborhood of K is torus, there is a meridian M, which is oriented like this. I mean, if we have a K with this orientation, the meridian rotates like this. Firstly, we consider such an object. We take arc from fixed point to the boundary and take meridian. And we define equivalence relation by homotopy, but the homotopy looks like this. If we have M, there exists alpha prime. Then if we can push alpha to alpha prime so that ends does not leave stay on the boundary, then we say alpha multiply M and alpha prime multiply R are equivalent. And now we take QK is the set of equivalent class of such a arc. And now we define binary operation alpha M star beta M phi beta M inverse beta inverse alpha M. Then what does it mean? Let's say here we have such a thing. For simplicity, let me do not draw boundary and star beta M alpha M. Then the star looks like first start from here. Oh, here beta M inverse beta inverse alpha. So beta inverse alpha and alpha. Oh, sorry, I made a mistake. Okay, beta M inverse beta inverse alpha M. Then you can see that we can push this part to here. So the alpha is equivalent to this part. And if you see this one as a crossing, the color of this part should be determined by this one and this one. So from the arc corresponding to this part and this part, as you see, this part is determined. To obtain such an equality, we give such a binary operation, then Q, K star is a quandle. And as a lemma, if K and K prime are equivalent, then Q, K, and Q, K prime are isomorphic. And this is called not quandle. Then why this is important? Firstly, in natural way, you can change left element to this one. So there is a natural there is natural correspondence. Fundamental group of not and not quandle. And secondly, actually we say not quandle is an invariant for knots, but for two knots, if their knot quandles are isomorphic, then K and K prime are equivalent, or minus K and K prime are equivalent, K star, K prime equivalent, or minus K star and K prime equivalent, where minus K is orientation, reversing, and K star is mirror image. So knot quandle distinguish knot almost completely. If two knot quandles are same, isomorphic, then there are only four possibilities. So, oh, sorry. This is called almost complete invariant. We can distinguish it almost or. Well, our goal was to distinguish knots, but knot quandle theoretically can distinguish almost or. So for a while, knot quandle was popular. Became popular to study. But of course, it is just theoretically, but practically, to distinguish two knot quandles are really difficult. So it is not possible, practically it is not possible to use knot quandle directly to distinguish knots. But because of this fact, you can see the effect many people try to obtain invariance coming from by using knot quandles. Okay, I think that's all what I want to say today. And next time, I will show another invariant, which is called the Jones polynomial, and which is called as quantum invariant. And then next time, I will talk about the relationship with low-dimensional topology. That's all for me. I'm sorry for late. I finished a little late. Thank you very much.
No problem. Okay, thank you. Are there any questions? Okay, so then let's thanks to Kim,
Yes.
and we will be meeting again on next Tuesday at the same time. Okay, by that.
Thank you very much.
By then, bye bye.
Bye-bye.